Kanu is in the electrical engineering department, but is a physicist by training. Did her PhD at the University of Maryland, and meet me before coming here. Was a postdoc at Princeton, except that it was COVID, so that was also in Maryland. And now she's here, and she's going to tell us about her work on quantum optics and cloud integration.
Thank you. Thanks a lot for the introduction, Will, and thanks for having me here, all the way from Goldwater. It's a great pleasure to be here. So I'm going to tell you today about quantum fluctuations, or nothing, and some ways to tame quantum fluctuations in nanoscale quantum systems. Or in other words, what we're trying to do is something about nothing, okay? And to start with, what are quantum fluctuations? So actually, if you look at QED, in empty space that is devoid of all matter and all radiation, nothing is not really nothing. There are virtual photons, particles that come from nowhere and go back to nowhere. And this is happening all the time, all over the place as we speak. And these quantum fluctuations lead to effects that we call as fluctuation phenomena. And they have consequences that range from all the way to this. Let's see if this moves. Okay, I'm having trouble with this clicker, so I'm gonna, finally. Okay, so these quantum fluctuation phenomena range, all the way from the scale of the universe down to the atomic scale. So here, what you're looking at is a baby picture of the universe from only, 380,000 years after the universe was born, where you can see the fluctuations in the temperature or the density distribution back in the day. And these fluctuations is what led to eventually the formation of galaxies, stars, and eventually us. And these early universe density fluctuations are attributed to quantum fluctuations in the inflationary phase of the universe. This was work that was done by Paul Davies, among other people. And here's a nice quote from Paul's latest book, which says that quantum fluctuations in the very, very early universe are written large and frozen in the sky for all of us to see. So this is the grandest scale possible where you can see quantum fluctuations. Coming to somewhat more perceptible scales, we have geckos. And actually, I'm gonna not use the clicker because this doesn't seem to work. So here, what you're looking at is a gecko. And if you've seen how geckos climb on a wall, there's the mechanism by which they stick to walls is actually they have teeny tiny hairs called setae that have a van der Waals adhesion that create an attractive force between their feet and the wall. Okay, and these van der Waals forces, they arise due to quantum fluctuations. There's some very interesting research going on in the field of what is called biomimicry, where people are trying to mimic similar, gloves with nanostructures for potentially humans to climb on walls and create gecko men similar to Spider-Man, perhaps. There's a relevant quote by the biologist who has been leading this field of study. Going to even more smaller scales, this is what I and my group study. We study atoms, and a lot of atomic phenomena that we know and love also arise from quantum fluctuations. So, for example, spontaneous emission, meaning that if you take an electron in an atom, excite it to a higher energy level, it will radiate on its own spontaneously and go back to a lower energy state. And this can be attributed also to quantum fluctuations. And if we look at the radiation from the sun, assuming that sun is an ideal black body, the most of the radiation in the visible range that comes is due to spontaneous emission. And in some way, we can say that spontaneous emission or quantum fluctuations are also, responsible for our existence in more ways than one. Okay. So with that, I want to come to the outline of what I'm going to talk about. So I'll start with an introduction to quantum fluctuation forces, or in other words, forces that arise from nothing. And I'll tell you about some ways to tame or tailor quantum fluctuations in nanoscale systems, which is what our research is about. And as an example of one of the ways with which we tailor quantum fluctuations, I'll talk about using quantum correlations or entangled states to tailor quantum fluctuation forces. Okay. All right. So to start with, how do quantum fluctuation forces come about? So here, what you're looking at is actually two objects, A and B, that are both neutral, and they're separated by the vacuum or nothing, that's my vacuum cleaner. And as these two objects interact, there are, tiny dipoles that constitute the two neutral bodies, and these tiny dipoles have fluctuations in them. And the quantum fluctuations of the field mediate an interaction between the fluctuating dipoles over here and the fluctuating dipoles over there, okay? And as these two objects interact, there is a force that arises simply because of the fact that there's an energy that depends on the separation between these two. And this is what we refer to as fluctuation forces, which we actually call by several different names, but they're all eventually one and the same thing. So they go by, London, van der Waals, Casimir, Casimir-Polder, depending on who you're talking to, who originally happened to discover, these forces in what context. Okay, so if we are talking about 2 point-like particles, we call it London or van der Waals. If it's a gecko climbing on a wall, we call it van der Waals. If we are thinking of two perfectly conducting parallel plates, we call it Casimir. And if we are thinking of, a particle or a few particles close to a macroscopic body, we call it Casimir-Polder. To give you a bit of historical context as to, how this whole thing started, this all started in the late 1940s with milk, actually. Not really milk, but colloidal suspensions. So in the late 1940s, Theo Overbeek was an experimentalist at Philips Labs who was studying, he and his team were studying stability of colloidal suspensions. So what are colloids? They are stable suspensions of, colloidal particles. And what they were trying to explain at the time is, can we, see, given what is the typical distance between colloidal particles in a certain suspension, can we understand why this is stable or not? And what they found is that their measurements of the interparticle separation were such that if you assume the quasi-static London theory, which doesn't include the retardation effects of the electromagnetic fields, you see that there is a 1/r⁶ scaling. So in other words, you get the wrong scaling without including the finite speed of light. And what Casimir and Polder did at the time was to write a quantum electrodynamic description of these interparticle forces, which were able to predict the correct scaling of forces such that these colloidal suspensions could be understood why they're stable. Okay, so the origins of this whole thing go back to the very mundane problem of trying to understand why is a certain colloidal suspension stable. And this actually, if you run the numbers for milk, it so happens that you do see that if you include the interparticle scaling as given by the London force or the London potential, it does not give you, milk would just clump together. Okay, so if, in other words, we did not have finite speed of light, milk would not exist. That's my claim. And so causality, thanks to causality, we have milk. Allegedly, after writing this paper in 1947, Casimir went on a walk with Niels Bohr, and he mentioned his results to Bohr, and Bohr mumbled something about 0-point energy. And this led Casimir to think in terms of, quantum vacuum fluctuations, and he wrote his very famous paper, what is now known as, named after Casimir as Casimir effect. So it's just 2 pages that you can see here. Actually, there's a little half a page over there as well, but the main result is all contained here. And what the calculation that he did in this beautiful paper is something like this. So if you essentially take a cavity of 2 perfectly conducting parallel plates, and you write the energy of the electromagnetic field modes with and without these 2 plates, the difference in the energy, because of the plates being there and the plates being not there, can be summed over. And you see that this difference actually results in an energy that depends on this separation, unsurprisingly. And if there's an energy that depends on the separation between these plates, we get a force which happens to be actually quite small. So of course, it's a force from nothing. So it's not surprising that the magnitude isn't quite large. So if you, to put some numbers, if you take 2 1 centimeter by 1 centimeter plates, as he illustrates in this paper, that are separated by a micron, the force is about 0.0139. I have no feelings for what that number means. So if you don't either, this is roughly the 1,000th of the weight of a housefly. Okay. And so, as he said in this paper, the effect is quite small, and the experimental confirmation seems, but it seems not unfeasible, and might be of certain interest. And it's certainly of great interest now, and has been since the early 90s, actually. So people started looking for these forces in the 1950s. The first experiments were done by Sparney, and what Sparney was doing is, looking at forces between 2 metallic plates. And of course, you can imagine that if you have 2 metallic plates, they're hard to kind of align parallel, because they're, two things are hard to align perfectly parallel. And what he observed was that these attractions, this was the conclusion of the paper, that the observed attractions between these plates did not contradict Casimir's predictions. Okay, so it wasn't quite an agreement, but it was at least not a contradiction. Later, there were other experiments with dielectrics based on Lifshitz theory. Lifshitz extended Casimir's theory to include dielectric materials and more realistic materials. And they cleverly used a sphere plate geometry. And the nice thing about spheres is that you don't have to worry about perfect alignment. It can, it is always aligned, however you have the sphere, right? In the 90s, in the late 90s, there were very precise measurements of Casimir force, first done by Lamoureux and Mohideen in the later year. And these were in agreement with the theoretical predictions, with up to 5% or few percent of the theory. And actually, these forces were also studied in the context of looking for extra-dimensional physics and short-range gravity measurements, because when you try to put 2 objects at short distances and measure gravitational forces, of course, electromagnetism is much stronger than gravity, and you inevitably run into these forces before you run into gravity. So you have to systematically characterize them, get rid of them somehow. And I know some people who have actually started out as gravity experimentalists and then later turned to, later become full-time Casimir physicists as a result. So these forces have also been measured with atoms. So this is an experiment which was done in '93, where if you send a stream of atoms through these tilted cavity, you can see the deflection one way or another as a result of the atomic interaction with the two plates, and characterize the atom wall force as a result. Now, where we are today, so of course, all these measurements back in the day and most of the recent years have been done with objects that are typically two classical bodies. And what I'm interested in is to look at what if one of these objects becomes a quantum system. So if we are thinking, of a typical nanoscale quantum system, where we have, let's say, a collection of atoms or solid state emitters, which behave in quantum, which have quantum properties. And this thing is placed near a macroscopic body, let's say a distance of few to few hundreds of nanometers. And this could be an atomic chip or a waveguide or a resonator. And we would like to understand how do quantum fluctuation phenomena arise in these systems. And there are two reasons why one might want to do that. So reason number one is because these nanoscale quantum systems are important for applications in quantum information science. You want to, couple your qubits to a waveguide, so you better couple an atom to, a waveguide or something. And as you go close, you run into quantum fluctuation phenomena. So that's one reason to care. Another more fundamental reason is, well, we've so far talked about quantum fluctuation phenomena with objects that have classical like boundary conditions. So there's a field that goes to zero here, or you apply some boundary condition. These quantum systems allow for the possibility that you can prepare them in superpositions, meaning they can be here and there at the same time, or they can be in two different states at the same time, or they can be entangled with each other. And these sort of exotic boundary conditions that are allowed by quantum systems open, new sorts of questions for us to explore in terms of quantum fluctuation phenomena. Okay. A little more about why we really want to go nanoscale. Why nanoscale quantum systems? The reason for that is in most of these applications of quantum science, in particular quantum information science, what we very much need is strong interactions between what we call our qubits or atoms and photons. And if we want to have those, we need to confine our electromagnetic fields in smaller and smaller regions so that our atoms and photons can see each other better. So just because they're confined in a small space, there's more likelihood that they will interact, right? And doing so brings us to a family of nanoscale quantum systems. So this is just some few examples where you have atoms coupled to optical fibers, photonic crystals, atomic chips. And in most of these cases, you encounter atom surface interactions at nanoscales. What I've drawn here are some theorist cartoons, but these ideas are not just theoretical. These are they've very much been experimentally realized in labs, and in some cases by butterflies as well. There's a photonic crystal structure in the wing of this morpho butterfly, which gives it this cool iridescent blue color. And they're also useful. So it's not just that, these things have been done for just fun's sake, but also you can make single photon devices out of these. You can sense gravitational fields and do other sorts of interesting applications. On a more practical side, why do we want to go to nanoscales is if you go to a typical quantum optics lab, this is what it looks like. It's a jungle of big, bulky optical elements. As a theorist, that's what it looks like to me. So you want to shrink this down to the size of a chip. And as you do that, you run into quantum fluctuation phenomena, which influence how you trap your atoms, how these atoms decay, how they lose their quantum coherence, and all these effects, all these aspects we would like to have some control over. To get you some intuition on how large these effects are, we can think about this very cartoon picture of a atom, which you can think of like a dipole in front of a mirror. So this is a dipole staring at a mirror. And if there's a dipole staring at a mirror, you can think of this in image theory terms. There's an image over there. And the interaction between the atom and its image goes as 1 over z cubed. We know from image theory. And this needs dimensions of energy. The only energy scale that we know in this interaction, as far as the interaction between the atom and the vacuum is concerned, is h bar gamma 0, where gamma 0 is the rate of spontaneous emission for this atom. Okay, it's still not the right dimensions. We need a length scale, actually. So if you look at the denominator, we need to make it dimensionless somehow. And we can do that by adding a length scale. And the only length scale we know in the problem, the only meter stick this atom has, is its own transition frequency. So adding that, you can actually get very close to the exact ground state potential of a 2-level atom in the near field regime of a perfect conductor. So this is the exact expression with that 1 over 16. Okay, I can also explain that later if you're interested. And if you plug in some numbers, so say if you're looking at a rubidium atom, which is the workhorse of most AMO experiments, at 10 nanometers away from a surface, you find this potential to be significantly large, that it overpowers all of our conventional ways of trapping atoms just trapping atoms using external lasers and fields. And this, this is a picture which shows here is where most of the near surface traps are, and at around 100 nanometers, fluctuation forces dominate. So we need to come up with ways, therefore, to be able to control and engineer these fluctuation-induced forces. And not just that, maybe we can also leverage the distinctly quantum properties of our atomic system. So maybe we can use the fact that these atoms can be driven, can be created in superpositions, et cetera, to create new kinds of traps. Okay, and this brings me to the next topic, which is how do we tame quantum fluctuation phenomena in nanoscale systems. So I'm taking an open quantum system perspective, meaning that we have our quantum system of interest, which is these bunch of atoms or whatever that might be, which is interacting with the electromagnetic field, the vacuum electromagnetic field, which acts as the environment in this case. So most of the quantum mechanics we study involves closed quantum systems. So you don't typically think of an environment, but here we are coupling this to an environment, and the environment is shaped by a bath. The environment is shaped by the presence of a boundary condition, which changes what the density of modes of these electromagnetic field is like. And as this system and the bath interact, you get different fluctuation phenomena. You get fluctuation forces, and also you lose energy to the environment. So that is dissipation. You lose your quantum coherence, which is the phenomena of decoherence. And you can see in this picture how to tailor these. For example, one thing you can do is you can change these, you can do something to the boundary condition. You can change the optical properties of the surface or the material properties or the geometry, and that will modify all your fluctuation phenomena. You can also change the system bath coupling. For example, you can use magnetic interactions instead of electric dipole, potentially. The more quantum things to do is you can drive the system to some non-equilibrium steady state potentially, which can also change how your system interacts with the environment. Or you can use quantum correlations or entanglement within the system that also changes how your system interacts with the environment, okay? This is by no means an exhaustive list of the number of things you can do to tailor fluctuation phenomena, but this is some of the ways that we've poked at the problem, okay? And what this is basically we are combining the framework of quantum electrodynamics in the presence of surfaces and boundaries with an open quantum system perspective where we think about engineering quantum states of different sorts together to come up with ways to coherently control our good nanoscale quantum systems that we like. So we've looked into some of the problems along these directions, which range from trying to trap atoms using nanoscale forces, quantum fluctuation forces, to how quantum particles get kicked around and exhibit Brownian motion as they interact with quantum and thermal fluctuations. We've also thought about how to shape interparticle potentials using some of these ideas. And I'm more than happy, since I'm a local, I'm more than happy to chat with you all about any of these ideas if you're interested. So please write to me and I'll be happy to talk more. Okay. So to get a bit more into how do we tame quantum fluctuations? So the first, as I said, the effect of one can change the properties of the surface, which is you can change its material properties and geometry. And here's a very nice review article from 2021, which summarizes different ways one can do that. I'm going to talk about a couple of examples regarding dielectric response and geometry. So this is this was an experiment done in 2009 at Harvard and Capasso group, where they demonstrated levitation of a gold nanosphere above a silica surface. This picture is, by the way, the poster child of all Casimir workshops. So if you go to one, this is likely what you're going to see on the poster. What's going on here is that you have two situations, one where you have a gold particle above a silica surface and a gold particle above a gold surface. In one case, you see that there's a repulsive force, and in the other case, there's an attractive force. And there is a reason, the ordering of these three, so you can think of this as object A, object B, and there's a medium in between. If you have a certain ordering of these permittivities, you can get repulsive interactions between objects. And that is what's happening in the case of gold and silica. If the permittivities of the two objects, epsilon A and epsilon B, are either both greater than or less than epsilon M, then you get attractive interactions. I'm just stating this without giving any reasons. And the idea, actually, you can, of course, see from here, because vacuum has the lowest permittivity ever, you're never going to get repulsion in between two objects in vacuum. So this also leads to sort of a no-go result at the same time. Now, the reason why they could order in this experiment the permittivities in such a way was because the two objects were not actually separated by vacuum, but by a weird liquid. I think it was bromobenzene or something like that. And that is what allowed them to be able to levitate this gold nanosphere above the silica surface. So that's one example of using the surface optical properties to tailor fluctuation forces. You can also nanostructure your surface. This was a paper which showed that by nanostructuring this grating, you can engineer the force between this metallic slab and the sphere. You can actually reduce it by a lot. So if you see, the unstructured sample is over there, the black dots, whereas by structuring, you can reduce the force to about a fourth of its original value. So that's quite significant and dramatic change that one can get from tailoring the geometry. You can also change the coupling between your system and the environment, as I said. And one way you can think of that is by thinking of magnetic dipole interactions in addition to the electric dipole interactions. And magnetic dipole interactions actually lead to repulsive forces. And why is that? You can see this from, again, an image theory argument where if you look at the image of a dipole staring at a mirror, it's similarly aligned and therefore attractive. The image of a magnetic dipole, on the other hand, is turned around and therefore repulsive. So this can inspire one to ask, can we stably levitate a magnetic particle above a surface? And I did ask that question. So the short answer is maybe with a really, really large spin particle. And the reason for that is magnetic interactions are inherently weaker by a factor of fine structure constant compared to electric interactions. So, well, if you have a particle with a spin 10 to the 4, then sure, you can do that. But more likely than not, you may not be able to. Another way that we said to tailor quantum fluctuation phenomena is to use external drives, or you can shine a laser on your quantum system, and that can change your fluctuation forces. And this is something that was not pointed out until really 2018 in this paper from Stefan Buhmann's group. And we also studied this in some other contexts. So why do you expect actually that if you shine a laser on a particle, why do you expect that this would have a different contribution in terms of its fluctuation force? We can kind of see that from this cartoon picture, where what I'm drawing is that you have the interaction between your particle of interest, let's say, which has a polarizability of P, and it's interacting with the electric field E. Each of these, the polarization and the electric field, are composed of now a classically applied external field and a classically induced polarization. At the same time, you have a fluctuation. You have fluctuations in the vacuum electromagnetic field and fluctuations in the polarization of the particle. You can see that if you look at the interaction between the classical terms, you get the classical trap potential, which we know very well. If you look at the fluctuation terms, you get the Casimir potential, the regular, garden variety. There are also cross terms. So you can get these interactions between the classically induced dipole on the particle, and that as it's interacting with the fluctuations of the field. And at the same time, you have a fluctuating dipole that's interacting with the classical laser field, okay? So these cross terms is what is responsible for a drive or an external field induced contribution to fluctuation forces, which can be actually pretty dramatic. So we are currently looking at this in an experimental setup in collaboration with the group of Markus Espelmeyer at Vienna. And in this system, what we have actually is 2 silica nanospheres that are each trapped by laser fields. And the idea is to bring them closer together and see if we can engineer, and how can we engineer their interparticle interactions, okay? What we've shown, and this is something that came as a surprise to us, is that if you bring these particles close enough and with the right parameters, with the right strength of driving, polarization, blah, blah, you can actually create bound states of as deep as 200 Kelvin. So it's kind of like a room temperature molecule of 2 dielectric silica particles, if you will. So we are currently excited about this, and we're also exploring different quantum states of the field along this line of exploration. I want to get to the next part of my story, which is using quantum correlations to tailor quantum fluctuations. And the idea here is that quantum systems can behave in a collective manner if you make them correlated or anti-correlated in a certain way. And this idea has been known in the context of spontaneous emission of atoms. So if you have a collection of atoms, each of which independently emits at a rate gamma 0, you can prepare these atoms in a collective state where all of these dipoles are radiating in phase. And that state is also known as the superradiant state, and you can enhance this emission rate by rate n gamma 0, okay? This is a constructive enhancement of the emitted radiation. And similarly, if you make these dipoles anti-correlated, you can suppress the collective emission down to a rate of 0, and these states are known as subradiant states. This was first pointed out by Robert Dicke, who is also, by the way, instrumental in the discovery of the cosmic microwave background, separately also the discovery of lock-in amplifier and a number of other things. So what was surprising at the time is that spontaneous emission is, thought to be something of an incoherent process, but it's actually not. You can see interference-like behavior in this somewhat seemingly incoherent process. What the intuition that we had is that what if you put these collective states near a macroscopic body, and if you now look at the forces, the fluctuation forces on these collective states, what you find is that the net vacuum-induced, the fluctuation force on these states gets enhanced or suppressed, similar to what you would expect in the from their spontaneous emission behavior. So this goes to the intuition that spontaneous emission and quantum fluctuation forces are kind of, counterparts of each other, and that's what we make use of here. Just to give you a brief, inside view of what's going on here, the idea is that if you have atoms that are in the ground or excited states, the corresponding, the processes that lead to their fluctuation forces are something like this. So an atom from ground state can jump to an excited state, emitting and reabsorbing a photon. And this kind of a process leads to corrections to its ground state energy, okay? Similarly, an atom that's in an excited state can go down and jump back up. This leads to modifications of its excited state energy. But if it's up there, there's no problem. It can emit a photon and go down because there is a resonance. So this additional contribution is actually what's responsible for the phenomena that we observe. What can happen is that if you prepare these two atoms, now imagine you have a red atom and a blue atom prepared in a correlated state, which is the blue is excited, red is ground, or blue is ground and red is excited, with a plus or a minus sign, okay? And the processes that can take place here is that these two can exchange a photon that goes off of the surface, and these two processes can interfere either constructively or destructively with each other. And this constructive or destructive interference of the processes is what leads to an enhancement or suppression of their surface mediated force, okay? We see this more explicitly if we write, the expression for force, depending on whether they're positively or negatively correlated, you see an enhancement or suppression. I'm not gonna go into the details of what each of these terms are, but this collective force, as we call it, is exactly it mirrors the collective spontaneous emission from these atoms as well. What I'm plotting here is that if I had prepared two atoms near a surface with some typical numbers, let's say in a what we call as a super radiant state, positively correlated, you see as the atoms get closer and closer, there's an enhancement in their collective spontaneous emission rate, as well as in their attraction towards the surface. Okay. More interestingly, though, if you were to prepare them in a subradiant state, aka they don't want to interact with the field, you can suppress both. You can actually suppress their, collective emission, so you don't lose coherence that way. They live for longer, and you can also suppress the attraction between the atoms and the surface. And this might be something potentially useful for trying to build atomic traps near surfaces and have your atoms live for longer. And that's an area we are currently exploring. So long live the dark state, indeed. Okay, in terms of where one might see these effects, there is one can think of systems with solid state emitters, where, for example, you have this chunk of nanodiamond which has defects inside it, and what you can do is you can shine a laser, as I'm doing right now, and excite all these emitters to their excited states, and as they trickle down to their ground states, they go through the superradiant state somewhere in between. And as that happens, we would observe a characteristic boost in the force on this nanodiamond, say if you were to put this on something like a cantilever. And that boost can be detected, I'm told, by my experimentalist friends. And if someone's interested in doing this, I would be very happy to talk to you. So there is potential avenues for observing these effects in solid state systems. It's actually not too far from some of the observations that were made. This was a paper from, I think, 2017, where people saw similar, nano diamond thingies with embedded emitters that exhibited an enhancement of their, if you trap these nanodiamonds with laser fields, you see an increase in overall trapping strength, which was attributed to these collective effects. And if you take a similar nanodiamond, put it near a surface on a cantilever, you might also observe a similar enhancement in the Casimir force as well. While we were studying this, actually, there was a very interesting experiment by some of my colleagues at University of Maryland, where they observed collective effects near optical fibers. So there was a bunch of atoms coupled to an optical nanofiber. So what you're seeing here is a regular fiber which is kind of stretched thin in the middle. And in these experiments, when I learned about this, I got pretty excited for obvious reasons, because you have collective effects near surfaces. So maybe we'll see something. But it turns out not quite, because the atomic gases are really diffused and it's hard to define where the center of mass of the thing is. But nevertheless, as we started looking into the system, this kind of led us into a rabbit hole. So the title of this paper, as you can see, is it's called Superradiance Reveals Infinite Range Dipole Interactions. And the idea where this title came from was that they took kind of two atomic clouds in this experiment, and they separated them by different distances and observed that, oh, the collective behavior doesn't change. So therefore, infinite range interactions. We actually started questioning that. Does it? What if you take these atoms really, really far apart? And it turns out that there is there's an interesting slew of effects that arises. So this is a bit of a rabbit hole that we got into, which is that, well, if you take these atoms really, really far apart, you start to invoke the memory effects of your environment, or something that we call as non-Markovian effects. And finally, without giving you any details here, you can enhance super radiance beyond regular super radiance to what we now call as super duper radiance. So this is a whole set of other things that we are working on right now with my group. You can form bound states of photons and atoms, and you can actually show that dipole-dipole interactions in 1D are in fact not infinite ranged because of these memory effects. And currently, we are working with the group of Steve Ralston at Maryland, where we are exploring a similar setup with 2 optical nanofibers now, and trying to actually hunt down super duper radiance. And the experiment, meanwhile, we found some other fun things, which is you can have collective effects in quantum beats. These are my collaborators on the experiment. Aryum is visiting us right now from Maryland, and she's actually going to give a talk tomorrow at 11 if you're interested in these topics. And what I wanted to say here is, okay, so I'm going to get to the summary. So what I've told you so far is that quantum fluctuation phenomena are ubiquitous in nature, from all the way to the scales of the universe down to atomic scale, and they play an important role in several nanoscale quantum systems that are important candidates in developing all sorts of quantum technologies. There are ways to engineer these quantum fluctuation effects using different methods, like engineer surface properties, control the interactions, change the direct interaction between system and bath, driving systems, and using external lasers, and preparing your quantum systems in entangled or quantum correlated states. Going forward, we are currently exploring a few different directions at the moment. So one that I'm particularly excited about is trying to explore the limitations to how large how macroscopic a quantum system can you make, and how do quantum fluctuations limit you in that regard. So here is a picture of what I call as the cube of physics. This is taken from Tony Z's Gravity in a Nutshell book, chapter 1. And what you're seeing here is, here you have this 3 fundamental constants, G, H bar, and C, and then you go from Newtonian mechanics, Newtonian gravity, there's GR, and all the way over there is quantum gravity, which I know nothing about. So, but there's this corner, which is less explored. This is at the intersection of H bar and G, where we try to think about massive systems that can be prepared that can behave quantumly. So one goal of that regime is to, make large superpositions of massive objects. And in that spirit, there was a very nice experiment by my collaborators in Vienna, where they were able to bring a dielectric bead of about 100 nanometers to its center of mass ground state. So that's pretty fascinating. And what we want to understand is, if you, in a very idealized situation, if you take away all possible sources of decoherence, are you eventually limited by quantum fluctuations at the end of the day in some way, in preparing large quantum superpositions and such? We are also exploring in that same system, can we prepare entangled states of these 2 nanospheres, and if so, how do potentially quantum fluctuations limit us in that regard? Another interesting experiment that I'm currently involved with and recently started working with is this one in Paris, where they studied, this is the group of Gabriel Duthier at LPL in Paris, and what they study is that they send an atomic beam through a diffraction grating, and you get a diffraction pattern. And this diffraction pattern contains signatures of the interaction between the atoms and these nanograting walls. So you can deduce what, for example, were the Casimir polar forces. Now, this is a very interesting problem because this lies in the regime where, on the one hand, you have this solid grating object, and on the other hand, you have this very delocalized atomic cloud. And how do you describe the interaction between this diffused, delocalized object and the grating is, it brings us to, this whole question of how to do Casimir physics with quote unquote quantum objects. We also are looking into, within this experiment, what if we excite these atoms? How do driven atoms, experience Casimir forces? Or what if we prepare atoms in collective states, and how does that change the atom surface force? So these are all the questions we are interested in at the moment. I'd be happy to talk about any of these ideas with you all. And with that, I'd like to thank you for your attention. And while all this work is about vacuum, this was not done in vacuum. So I thank my awesome collaborators who have been a part of all this.